The learning objectives this time are to define what a titration is, to recognize titration curves for various types of acid-base titrations, and draw titration curve for strong acid, strong base titration and label the key points. And calculate the pH of key points along the strong acid, strong base titration. Okay, so titration curves, what is a titration? A titration is a procedure for determining the concentration of an unknown solution by adding a solution of known concentration. And you don't necessarily know the amount of it, but you know what it is. And you know there's some reaction that you're gonna add something in solution that will cause that reaction to trigger, and you can tell when the reaction has finished. And by doing that, when you know you've added enough to know that the reaction is finished, then you can determine how much was in there. Yeah, so you add this known concentration solution until some change indicates stoichiometrically equivalent amounts. What is the some change? Well, it totally depends on what the reaction is. There's lots of different types of titrations. And we looked a little at this at the beginning of the course. We're going to be talking specifically in this case about acid-base titrations. And so you'd use an acid to titrate an unknown base until we reach the equivalence point and know how much base we have, or alternately use a base to titrate an unknown acid. And the reason we can do this, there's going to be some change that happens. And as you can guess, it's going to be the pH. So if we have a way to detect changes in pH, we can tell how much acid or base we have. And so what we use to do this are indicators. So indicators are a chemical that changes color when the pH changes. Why do they change color when the pH changes? Well, it changes colors because the energy level it absorbs, the energy levels it absorbs change when it is protonated or deprotonated. The chemical structure changes, usually by changing the number of conjugated bonds in the molecule. It changes when a proton pops on or off. And these indicators are all weak acids and weak bases. And so they protonate or deprotonate at specific pHs. The indicator colors usually change color over 1 to 2 pH units. And of course, 1 to 2 pH units means a change in concentration of H plus or hydroxide by 10 to 10 to 100 times. That seems like a really big change. So can we really make precise determinations of how much acid or base there is based on a change of such large concentrations? So we'll get to that in a second. Here's an example of methyl purple. When it's acidic, it's purple. When it's basic, it's green. And there's a whole range of commercially available indicators that cover a whole span. Usually when you have pH paper, that's actually a combination of, the paper is soaked in several different indicators. So you get a color change at a range of different pHs. Some actually have 2 deprotonations, so you get 2 color changes. Most just have 1 color change. So there's a wide range of things that can be used. Okay, so let's start with the simplest titration, a strong base added to a strong acid. So what happens? Well, you start out, let's say we start here and we have a solution of 40.0 milliliters of 0.1 molar HCl, and we're titrating it with 0.1 molar sodium hydroxide. So we have a strong acid and a strong base. So clearly when we start, we're going to have a very low pH. And as we add sodium hydroxide, it's reacting with some of the acid. However, you remember pH is logarithmic. So when we only have half as much acid as we did before, so we've reached essentially the half equivalence point. The pH is only changed by about log 2, right? Because the concentration of H plus is only changing, if it changes a factor of 2, it only changes log 2, which is about 0.3. So not much is changing. However, once you get very close to adding exactly the same amount of base that you had acid, once you reach the stoichiometric equivalence point, well, we know at the equivalence point, then the acid and the base will be completely neutralized and we'll have pH 7. And so the equivalent, so somehow it's going from very small changes in pH to a huge change in pH. And then once we've added a lot of NaOH, any additional NaOH we add, all the acids reacted. So all we're doing is gradually increasing the concentration of the sodium hydroxide. And again, if we double the amount of sodium hydroxide, then we only change the pH by 0.3. So it's changing very slowly until all of a sudden it changes a huge amount and then it changes very slowly again. And so that's why we can do titrations and get very precise measurements of how much the unknown amount of the concentration of acid or bases, even though indicators take 1 or 2 pH units to change, is because when you are near the equivalence point, you have huge changes. A way to think about it is, when we've taken up 95% of the acid, the pH is changed by log 20, which is about 1 or 1.3 or so. But when we've reached 99%, then it's changing by log 100. That's changing by pH of 2. 99.9, we're dealing with a log of 1,000. It's 3. So that's a 9. So you can see that the pH only changes as you get very close to, it changes drastically when you get very close to 1. So that's the key, is that because it's based on essentially logarithmic concentrations, you have a very large change of pH when you have a strong acid and a strong base reactant. So, a small amount, going from 99.9% of the acid used up to 99.99% of the acid used up, you only change by pH 4. So once you get close to neutrality, a very small change in the amount of base added makes a huge change in pH. You can say, bingo, that's the equivalence point. I know very precisely how much base I needed to add to neutralize the acid. So that's how titrations work. Because of the chemistry of the concentrations, you get a huge pH change when you are near the equivalence point, i.e. when you've added the same amount of acid as base. Remember, for all of this, the only actual reaction that's occurring is hydroxide plus hydronium goes to water. The counterions of hydroxide and of hydronium are just solvated. They're just doing their own thing. Yeah, and so the equivalence point, again, that's the definition when all of the initial reaction has occurred. There might still be some equilibria happening, but the initial reaction that you put in has completely happened. So let's look at a few other, we'll survey all the different possibilities here. So we were just looking at this case, an unknown strong acid titrated with strong base. It starts quite low. How low depends on what the concentration is, but it changes gradually until you get near the equivalence point. The pH shoots up, and then it ends up quite high. So again, this is the equivalence point when we've added stoichiometrically just enough for the reaction to occur. Notice that here, when we've added the half equivalence point, the pH hasn't changed very much. It'll change by about log 2. It'll change a little more than that because you're diluting it as well, but it'll change by about 0.2. And that'll depend on the relative concentrations of what you're adding. Unknown strong base would be exactly the opposite. We have start out with something very basic, and the pH stays pretty constant until you get to this point. It drops a huge amount, and then it stays relatively constant. A way to think about the equivalence point is it's where you've had a complete reaction of the acid and base to form a salt. So if you have a strong acid, a strong base, you have a neutral salt, at the equivalence base point, the pH will be 0. Okay, so those are pretty straightforward to do. What's more complicated is an unknown weak acid titrated with a strong base. Obviously, it's a weak acid. We're going to start with an acidic solution. The pH will gradually go up. And interesting, like here, you get a little plateau right about the half equivalence point, which is the volume that is half of the equivalence point. And we'll see a little bit later why that's so flat. In fact, it'll go through sort of a complete, it'll be completely flat for a minute before it starts going up again. The equivalence point, it's a weak acid with a strong base. So at the equivalence point here, it would be equivalent to all of the base being consumed. And so you have a basic salt. Weak acid, strong base, a basic salt. So it's sort of like you've added a basic salt here. And then after the equivalence point, then it goes up pretty quickly because all you're doing is essentially adding more base. And so it gets pretty steep after that. Note that these curves are not quite as steep as they are for strong acids and strong bases, and that's because it's a weak acid. It's a little less sensitive to changes in the pH. If we have an unknown weak base, then we titrate it with a strong acid, we get the exact opposites. It starts basic. You'll have a plateau here, and then it will quickly then it'll continue down. At the equivalence point, it will be acidic because you've essentially consumed all the base, so it's the equivalent of dissolving in a basic salt, and then after that, it just goes to be more and more acidic because you consumed all of the acid. You just have so you just consumed all of the weak base. You just adding acid. So all you're doing is making a dilute solution of acid with a little bit of acidic salt in there as well. And again, this place where it goes flat is the half equivalence point, and we'll see that why that's the case pretty soon. And I think those are the main points to go on here. See if you, as we think about it, see if you can think about what the pH would be at this point where it's flat. What is the pH going to be equal to at that